Specimen paper 1, 2014 AQA A-level physics. We're on to section B. This is the multi-choice section. The nucleus beryllium 9 captures a proton and emits an alpha particle. What is the product? So it's got 9 and 4. If it captures a proton, it's going to go to 10 and 5. If it emits an alpha particle, that's got to drop by 4, so that goes down to 6, and that's got to drop by 2, so that goes down to 3, so it's got to be 6 lithium. Which is that one. When comparing X-rays with UV, what statement is correct? X-rays have a lower frequency. No, they have a higher frequency, higher energy. X-rays travel faster in a vacuum. No, all EM waves travel the same speed in a vacuum. X-rays do not show diffraction and interference effects. Of course they do, because they are waves. So using the same element, photoelectrons emitted by X-rays have a greater maximum kinetic energy. Yes, because they have a greater energy themselves. Monochromatic radiation from a source of light is shone through a metallic surface, and electrons are emitted from the surface. When a second source, source B, is used, no electrons are emitted from the metallic surface. Which property of the radiation from source A must be greater than that of source B? So it's got to be the energy is greater. So the amplitude, no, that just affects the intensity. The frequency, yes, that affects the energy of the incoming photons. Intensity, no, that would just increase the number of photons, photoelectrons. And the wavelength, well, that does affect the energy, but it's the wrong way round. You need that to reduce to be higher energy, because shorter wavelength is higher energy than longer wavelength. High frequency, low frequency, higher energy. You can tell it's higher energy just because you have to scribble harder. 2 vertical copper wires, X and Y. There's X, there's Y. Of equal length are joined as shown. Y has a greater diameter than X. The weight is hung from the lower end of Y. Which of the following is correct? The strain in X is the strain in Y. Well, no, because this one's going to be, they're going to have this, if they're copper, they're going to have the same as Young's modulus, so there's no reason for that to necessarily be true. It might fluke it, but I don't know, probably not. The stress in Y is greater than the stress in X, definitely not, because they have different areas in the same. This one's got a bigger area, so its stress is going to be smaller. The tension in Y is the same as the tension in X. Yes, that's got to be true, because otherwise at the join here, they would fling apart. So the tension in both wires has to be the weight, which is mg there. So that's one is the true one. The elastic energy stored in X is less than that stored in Y. Well, again, don't really know, but if they're the same material, then they should have the same Young's modulus, which means that because this one has it's got the same force in as this one, bigger area, so that means the strain is going to be less. So the stress is going to be less and the strain is going to be less, so there's going to be less energy in this one than this one. Yeah, so that's the wrong way around. There we go. Keep going. Question 11. An electron has kinetic energy at E and a de Broglie wavelength of lambda. The kinetic energy is increased to 4E. What's the new de Broglie wavelength? Well, kinetic energy is a half mv squared. So if we times that by 4, that stayed the same, so that's gone up by 2, it's doubled. So V has doubled, so new velocity is 2V. De Broglie wavelength is equal to Planck's constant divided by mv. So if we double that, then we halve the wavelength, so it's got to be that one, B. The diagram shows 2 pulses along a string travelling towards each other. Which of the following shows the shape of the string when the pulses have passed through each other? So that's when they are passing through each other. They won't invert. It'll be that one there, that they're going like that. and this one, they won't stretch out at all, they just pass through each other and retain the same shape, so it's that one there. Question 13. Monochromatic light may be characterised by its speed, frequency and wavelength. Which of the following quantities change when it passes from air into glass? Okay, so, well, the speed definitely changes. Speed and wavelength. Well, the wavelength changes because V is equal to F lambda. That is fixed, so if the speed changes, the wavelength changes. So that one. Speed and the frequency, no, the frequency's got to stay the same. And the wavelength and frequency, well, the frequency's got to stay the same. Right, I'll just quickly explain why the frequency's got to stay the same. Well, if the light waves are entering one material and the frequency increases, then that means suddenly more waves are being created at the boundary. That doesn't make any sense. And if the frequency were to decrease, then that means a bunch of waves are disappearing and vanishing somewhere. So that doesn't make sense. So the frequency has to be the same. You have to have the same number of waves every second. In the photoelectric experiment, light incident upon the metal surface of a photocell is increasing the intensity of the illumination at the surface leads to an increase in the, well, you should know this straight away, intensity increases the number of electrons released. So it's more electrons means more current, so it's that one. Let's just go through the others and reject them. Work function is a property of the metal. The minimum frequency at which electrons are emitted, well, that's linked to work function. It's the phi is equal to F minimum H. The current's the correct one. The speed of the electrons, no, we'd need more energy in the photon, so we need a higher frequency photon if we wanted to increase the speed of the electrons or change the speed of the electrons. In the circuit shown in the diagram, the cell has negligible internal resistance. What happens to the reading of both meters? They've drawn this quite funny. They've put the resistor in the loop and the voltmeter across there. Normally you'd draw those the other way around. Never mind. When the resistance of R is decreased. Okay, so if the resistance of R is decreased, then that means the total resistance decreases, so the current has to increase. So A is going to increase. So it's either that one or that one. Okay, if the current increases, then that means that the potential across this one here has got to increase. And if the potential across this one increases, you've still got the same total potential. So that, the EMF, call that V1, call that V2, like so. The EMF is equal to V1 plus V2. More current means there's more potential across that one, so V2 is going up, which means that V1 has to go down. So it's got to be that one or that one, so it is B there. In the circuit shown, V is a voltmeter with a very high resistance. The internal resistance of the cell R is equal to the external resistance there. Right, so that means that the lost volts are going to be equal to the voltage drop across there. So they're going to be, the EMF is going to be split half and half because those two resistors are identical. Which of the following is not equal to the EMF of the cell? The reading on the voltmeter when the switch is open. Well, if the switch is open, no current flows. The definition of EMF, well, one of them is the terminal PD when no current flows. So that one is true. The chemical energy changed to electrical energy when a unit of charge moves through the cell. Well, that again is a definition of EMF, so that's definitely true. Twice the reading on the voltmeter when it's closed, when the switch here is closed. Well, as I said before, those two are the same, so they'll have half of it each. So that's true. So the electrical energy produced when a current passes through the cell, well, that's just nonsense. No electrical energy is produced, energy is transformed. So that's just bobbins, so that's false. Monochromatic light of wavelength 490 nanometers falls normally on a diffraction grating that has that many lines per meter. Which of the following is correct? Right, so for this one, you need this equation here, d sine theta is equal to n lambda, that's your diffraction grating equation. Right, the first order is observed at 17 degrees. So let's work this out now. Sine theta is equal to n lambda over d. So that's n lambda times by 1 over d. Well, 1 over d is the lines per metre, because d is the number of lines. So here goes. Right, so let's say n is 1 first. Lambda is 490 times 10 to the minus 9, and we need to times that by d, 1 over d, sorry, which is this number here. So that's 6 times 10 to the 5. And we get this. Okay, so that's the sine theta. So if we inverse sine that, we get 17 degrees. So the first order is at 17, that's correct. Let's just show that the other ones are wrong before we move on. You wouldn't have to do this in an exam because you have got the right answer, but I will show you. The second order of observed is that. Well, the second order will be when this n is 2, so it's twice as much as this. So sine of that, oops, inverse sine of that is 36 degrees, so that one's wrong. So get back our answer. The third or higher orders are not produced. Well, we divide that by 2 to bring it back, and then we times it by 3. This is the third order one. That's still less than 1, so we've still got an answer. Inverse sine of that, it'll be at 61 degrees, so that's false. The grating with more lines would produce more orders. No, it's the other way round. The grating with more lines per metre would diffract the light even more, so you might get fewer orders. So that one's false as well.